Okay, here is another exercise where we are to find out the potential and electric field inside an uniformly charged sphere. This one. So it's charges everywhere inside here, charge density. And it is a similar problem to the previous video, where I was looking for the potential inside, but then it was only a spherical shell. So there was no charge density inside in that case. And then the Poisson equation was just nabla square V equals 0. But in this case, for a uniform sphere, there is charge density inside. So then this is the Poisson equation. Negative charge density rho and E naught. And in the same way as in the previous video, let's look at the spherical Laplace operator. And it's like this, acting on V, the potential. And by symmetry, V can only depend on the distance r. There is no angular dependence. So, okay, this term and this term disappears, and we only have that term. So, the Poisson equation reads exactly like this. So, okay, multiply up r square. And, okay, so then there is the derivative here. I equal this and r square. So this guy here must be equal to primitive function to that when you have r square here. So you get r cubed over 3 plus a constant. So far so good. This is what we get. Okay, so then we divide by r square. Okay, so obviously, yeah, okay, r over 3, then constant a over r square. And then again, let's find out the primitive function. So it will be r square over 2, but there is a 3 here, so it is r square over 6 here. And then primitive function of that is negative a over r plus a constant b. So if you take the derivative of this, you will get back what you have here. So here is the general situation, how the potential must look like according to Poisson equation. All right, so let's start with the boundary condition when the r equals 0 in the center. Okay, so okay, then that is 0, and this term here blows up, so that's no good, and this is a constant. So in order to avoid that blowing up, then a equals 0. So then we're left with that one plus a constant. And okay, next, so that's what you have here. Next is boundary condition at the distance capital R here. So what is the potential outside the sphere or very close to the sphere? Yeah, we learned that before. It's just like you put all the charge Q in the center. So V equal Q over 4 pi E naught R, capital R. So that's what I'm saying here. So just outside the sphere on the border. So you have this. Okay. So then it should be equal to this here. Right. And yeah, okay, so I have put in the density here. Charge density is obviously the total charge divided by the total volume. So that's the charge density. Okay, we can write it like this then. So, all right, so then we put in that R equal capital R. So you, okay, only R here plus the constant B. And this can only be equal each other if B, this plus that, and that turns out to be this. Then we determine the constant B from that boundary condition here. And A was determined from that boundary condition. So let's see if we can simplify this a little bit. We know then is this plus the constant B that we just determined. And this can be simplified into that. So that was pretty complicated. So, but it is straightforward with Poisson equation to find out this result here. So that's great. So all right, the electric field, since it's electrostatics, the electric field is the negative gradient of the potential. And the gradient in spherical coordinates is just the VDR. And since V is not dependent on angles, the rest of the angles, the gradient terms depending on angles is simply 0. So this is the only thing which is of interest. So let's, okay, negative here, this is a constant, okay, and then let the derivative act on those guys here, the free will be 0, so you get, okay, negative 2r over r squared. And this, so that's the result. That's the electric field. And yeah, so electric field at the center r equals 0, so you see the electric field is 0. As expected. So this is a simple result. But let's look again at this result. This is a little bit more complex, not obvious to us, is it? So at the center, then R equals 0. So then potential is 3Q divided by this. That's what I write here. And what? Why is that? Can we understand this? So that's the potential at the center of a uniformly charged sphere. So why is that? But let's take a look at the previous video where we derived what is the potential inside a spherical shell. And that was just the charge Q over 4 pi E naught and the radius of the shell. And it doesn't matter where we measure it. For example, in the center, it was constant everywhere. So, okay, so let's look at this. This is the potential. It's one contribution from one shell. And this shell has a total charge dq, and its radius r here. So let's use the result for a shell, and then sum them up to get the total for a uniform sphere. So that's what I'm trying to do here, so we can understand this result a little bit better. So this is one contribution from one thin shell with charge dq. And the charge of this shell, that can be the charge density times the volume of that shell. So that's the surface area multiplied with the thickness, dr, which is thin. So this is the volume times the density. That's the Q in this case, and then this. And this can be simplified into that. And now we sum them up. Rho and E naught is a constant. Break that out from the integral. Sum them up. That's the same thing as integrating from 0 to R. All shells between 0 and R we're going to sum up by integrating. And then you get this result. So, rho, we already know the total Q over the total volume. That's the density rho. And then the E naught here, and then this. And what? It actually simplifies to this result here, exactly the same as here. So, okay. So now we found out by two different methods what is the potential at the center. So I guess it must be true then. And then you realize that this is not so easy to understand. This is even harder, right? but it was not hard to find out the result. It was just using the Poisson equation, which is very nice. Okay, thank you very much.